In a previous screencast, we looked at applying a steady state approximation to this overall reaction of 2A plus B going to the product A2B. And we looked at it for a sequence of elementary steps that are indicated here, where A plus B initially reacts to some reactive intermediate, AB star, and then that reactive intermediate subsequently reacts with A to make the product. And when we applied the steady state approximation, we got the rate expression as shown here. And the important thing to note is this is the rate expression at low concentrations of product. And so now what we want to do is say, suppose instead we apply the rate determining step approximation to the same sequence. And the way we're going to apply it, we're going to assume the second step. So we're going to assume this is the rate determining step, which means this must be, the first step must be in equilibrium, or refer to it as often as quasi-equilibrium. This is an assumption that we're making, and then what we want to look at is what does the rate expression look like? How does it compare to this steady state approximation? So we assume for step one that we're in equilibrium, which means we have some equilibrium constant that would be equal to concentration of AB star, concentration of A over the concentration of B. Product concentrations over reactant concentrations raised to their stoichiometric coefficients, which are 1. And this equilibrium constant is the ratio of these two rate constants. The rate determining step approximation says the rate that we're making our product A to B is going to be the rate of this second step, since it's the rate determining step. So that's AB star times A minus K minus 2 concentration of product. Again, we're going to look at low concentrations of our product because that's how we often run the experiments to make things simpler. So we're going to set this term to 0, and then we're going to substitute for AB star into this expression. So AB star is just the equilibrium constant times the concentration of A, concentration of B. So if I make the substitution of the rate constant, equilibrium constant, concentration of A squared, concentration of B, that's now the overall rate of reaction, low concentrations, for the rate determining step approximation. And so we can compare this now to the steady state approximation. What we see if we make the comparison, that the steady state approximation is the same as saying K minus 1 is greater than K2 times A. Or the other way of looking at it, if I multiply both sides by AB star, and you'll see why I'm doing this. So what this is telling us is that K1 times AB star, which is the reverse rate of the first step, the rate that AB star decomposes in the first reaction, is greater than K2 concentration of A to concentration of AB star. That's the rate of this second step, the forward rate. So what the rate determining step is saying is that we make AB star, it's much more likely to decompose back to the reactants in the first step than to react with A to make products. And so, indeed, that's what the rate determining step approximation is. The first step is in equilibrium. So make AB star is most likely to go back to A and B, and some small fraction will react with A to make product. And so we can see that the rate determining step is a subset of the steady state approximation, where we make some additional assumptions to get a rate expression that, if we have some basis for making the assumption, may correspond better to what actually is the measurement we make.